This is section 1.1, Inductive and Deductive Reasoning. On this slide above, you see a famous work of art. This is Auguste Rodin's The Thinker. The two pictures together pose the question, what separates humans from other species that occupy this planet? As you probably know, it's the ability to think critically, to problem solve, to process information and draw conclusions. Math is very important in developing these skills. Math plays an important part of your life. It helps you to understand logic, to problem solve, and to understand numbers. You may be solving an important problem, making an important decision, or simply trying to keep up with the daily news. Math also plays an important part in your career. The more math you know, the more career choices you will have, and the more money you can earn. This is true because throughout high school and college, math is often a required course. Therefore, the further you go in school, the further you've gone in math. This makes you more eligible for various types of jobs. You may want to be a doctor, a teacher, a scientist, an engineer, or any other profession. No matter what it is that you strive to be, you're going to have to be able to think critically. Mathematics and your world. Math can help you understand the world in which you live and allow you to form educated opinions on important issues. Perhaps you're interested in baseball or other sports. Statistics play a critical part in these sports. Perhaps you're interested in global warming and understanding the pollutants of our air. Perhaps you're interested in the population of animals or forestry. All of these issues involve critical thinking and problem solving. In order for you to form an educated opinion on important issues, you need to be a good thinker, and math can make you a good thinker. Inductive reasoning is one type of reasoning that allows us to be good thinkers. Inductive reasoning is the process of drawing conclusions based on experiences. From inductive reasoning, we draw conjectures. These are the conclusions that we draw. A counterexample is one case for which the conjecture does not work. Let me pose an example. Have you ever been to the Florida Keys? Perhaps Key West, in the southernmost point of the continental USA. Well, if you haven't, let's pretend that you're there now. You're in the Florida Keys having a great beach vacation. You're relaxed and laid back. Everybody you meet there is relaxed and laid back. When you come back to Pittsburgh, you tell all your friends about your great vacation and how everybody in the Florida Keys is relaxed and laid back. Your conjecture that everybody is relaxed and laid back is based on your experience. You're using inductive reasoning. However, there could be a counterexample to your conjecture. Perhaps on the last day of your beach trip, you run into a Key West resident that doesn't like the tourists. This Key West resident is frustrated and annoyed at all the traffic the tourists create. So all of a sudden, your experience that everybody in Key West is relaxed and laid back no longer exists because of this counterexample. Let's look at a numbers example, a math example with inductive reasoning. In this example, we're going to draw a conjecture of the sum of two-digit numbers. For example, if we take the sum of 22 and 10, both of these are two-digit numbers. 22 plus 10 is 32. Let's do another example. Perhaps 37 plus 15. Well, remember your addition. 12, carry the 1, 3, 4, 5, 52. Let's do another. 74 plus 20. The sum of two two-digit numbers, 94. Now, based on these three examples, or based on our experiences, we can conclude that the sum of two two-digit numbers is a two-digit number. Because, as you can see, 22 and 10 are both two-digit numbers, and it results in 32, a two-digit number. 37 and 15 are both two-digit numbers, and it results in a two-digit number. 74 and 20 are both two-digit numbers, and it results in 94, a two-digit number. So using inductive reasoning, we conjecture that the sum of any two two-digit numbers will result in a two-digit number. However, can we come up with a counterexample? Sure we can. For example, 99 plus 10. This is the sum of two two-digit numbers, and we know that the sum is 109, which in this case is a three-digit number. So all of a sudden, the conjecture from our inductive reasoning has a counterexample, and we must now understand that our conjecture was false. Anytime you identify a pattern, you're using inductive reasoning. Perhaps you remember taking your last standardized test, where there was a row of numbers and you were asked to find the next two numbers. That's identifying a pattern and using inductive reasoning. Perhaps there was a row of figures or shapes and you were asked to find the next shape. Well, they were testing your understanding of inductive reasoning. Let's take a look at a couple of these types of examples. For example, if we have the pattern 2, 4, 6, 8, 10, ... and you are asked to find the next two numbers, based on the experience of the pattern, seeing that these are all even numbers increasing by 2 each time, you would conclude that the next two numbers would be 12 and 14. You're using inductive reasoning. Let's look at another pattern. 2, 4, 8, 16, 32, ... Can you find the next two numbers in this list? Hopefully you've identified the pattern that the numbers are doubling. 2, 4, 8, 16, 32 double. So the next two numbers will be 64, because that's 32 doubled, and 128, because 64 doubled is 128. All right, let's look at example 4, finding the next figure. Say I gave you a pattern that looked like this. Square, circle, square, circle, square. What would the next figure in this pattern be? Of course, it would be a circle. You've used inductive reasoning to identify the pattern and make a conjecture that the next figure in this pattern would be a circle. Let's try another one. Here's the pattern. Can you find the next figure in this pattern? You got it. All the figures are squares, but as you can see, the tick mark is moving counterclockwise around the sides of the square. It started up top, then went to the left, and then the bottom, then the right, and now we would use inductive reasoning to conclude that the next figure would be a square with the tick mark on the top. Remember that inductive reasoning is when you draw a conclusion or make a conjecture based on your experience or based on a pattern. The other type of reasoning is called deductive reasoning. This is the process of drawing conclusions based on a general statement that you know to be true. In other words, drawing conclusions based on facts. The conclusion we draw when using deductive reasoning is called a theorem. Let's look at an example. Here's our fact. All college freshmen must take math. We know that Alberta Einstein is a freshman. What can we conclude about Alberta Einstein and math? You got it. Our conclusion, or our theorem, is that Alberta Einstein must take math. Based on the facts that we were given, we were able to draw a conclusion using deductive reasoning. This has been section 1.1, an introduction to inductive and deductive reasoning.